Okay, let's get started. Today, there's a simple title. What I want to do is talk about bond graphs. Now, there are two ways to approach this subject. One, you can get going pretty quick. You don't need to know that much, just a few ideas. And you can do this kind of hello world of bond graphs. There is some benefit to teaching it this way, because students can get going immediately. But the problem with this approach is that once you get stuck, you can't get yourself out of it. You know, and then you have to understand just a little bit more about exactly how these things work, what the meaning is of everything, etc., etc. And then the problem starts, and then a lot of students will say, well, had I only known this when I started this. So this semester, I'm going to turn it around. So what I want to do is, in lecture, go carefully through the foundations of this thing, exactly what is what and how it fits together. And then Thursday, we'll have a recitation section that will be led by Koen, where we'll be doing circuits and block diagrams and all the other tools that you have in your engineering arsenal where you can make, where you can model systems with. And then it will be more apparent how these bond graphs really bring it all together. All right? But rather than, so I'm gonna, from now on, we're gonna try to, for this period, we're gonna separate the presentation even more. So a purely kind of concept-based thing on the Tuesdays, and then applied, this is how you do it, nuts and bolts on Thursdays, okay? So with that in mind, I'm going to talk about these bond graphs. So let me get going. Let's give the point to the focus.
It should work. Does it work? Oh, maybe this where's the USB? Quinten, did you return that USB?
I returned it, but I think it's inside it.
Wrong way around, inside, jammed. Huh? Quinten.
All the viewers on YouTube.
Everybody on YouTube knows the Quinten's.
Yeah.
Fortunately, these lectures are recorded, so posterity will know that it's Quinten's fault that this all happens.
Try it.
No.
Moment. You want to try?
So I was not looking. Oh, here we go.
Yeah, that was me. Anyways, you can use the keywords. This one also doesn't work.
The keyboard also doesn't work?
These, yeah, so this works.
So what can I use? The one to the right.
This one. Somewhere.
Oh, right here,
Yeah.
right in there. Yeah, okay, great. Good. Okay. All right, let's keep going. So, first of all, I'm going to start looking at some engineering diagrams here and talk about these bond graphs. So, here we are. This is a system that we're talking about. There's a mass, there's a spring, and there are two dampers that I put here. So this damper here, you will all know how the system works. This damper is somewhat unusual. Let me see if I can get this. This damper here is somewhat unusual, but you can easily imagine how this works. All right. But if you think in a way, you get your normal mass spring damper system. This damper takes away from the momentum. The spring stores the potential energy, and the mass retains its kinetic energy, and the damper takes away energy. it does that by acting on the velocity of the mass, right? So here there is a certain velocity, and it has it in common, so it will generate a frictional force proportional to the velocity. This damper is a little bit different, right? So this one will react, there's a force going through here, and the force is transmitting the momentum of the mass to the wall here, and it will go right through this, this link here, the damper and the spring. So the spring and the damper are subjected to the same force. So the causality is the other way around. You start with a force, and the spring is going to, or the damper is going to start compressing at a rate v. All right? So this damper reduces the momentum at this rate. This damper reduces the deflection of the spring. All right? So we all know what this means economically. This is the demand, this is the price. This one discounts the price. All right. This here is your storage of inventory, and without the damper, you will just store everything that you're buying or selling, right? But the damper takes away some of it, so you get inventory shrinkage from the perspective of the inventory. All right. So this is our setup, and this is the system we're going to analyze with bond graphs. Now, bond graphs have been designed to be a general tool in which we can analyze systems. So this here is very specific to a mechanical system. But as you've learned in your mechatronics, you can also make an electrical system that behaves exactly in the same way. And I sketched this out. I bet you there's a bunch of mistakes in it, so probably the voltage is not right. I see this now, that should be over here. It should be there. But I think the spirit is okay. So this thing here will be okay. So the current is going through here. Under a coil, the inductor keeps the current going. The current is going to split into two, so that the current here is analogous to this velocity. It's going to split into two, so that is this damper. This is R2. And this spring is here, C. All right? Because the entire velocity of the mass is taken up by both the damper and the spring, and here the entire current is taken up by the current going in the capacitor, plus the current going into the resistor, and the sum of those is going to be the total current, right? You look really confused already. Yeah?
Yeah. If actually the velocity is split over the capacitor and the resistor, and in parallel the other resistors, so R2 should be parallel, while R2 and C should be in series.
Okay, so this is the interesting thing, right? So when you see, if you split the total velocity in two, you've got to put the elements in series. If you split the total current, you've got to put the elements in parallel, right? That kind of sucks, doesn't it? Right? Huh? I mean, it doesn't make it easier to see the analog, does it? So, inversely, this damper here is in parallel with this damper spring system, but here it's in series with the damper spring system. Correct? All right? So you see that to get this thing right, you have to take everything that's here in series and make it in parallel, and everything that's in parallel here, you've got to put it in series. All right? Yes?
The causality of R2 is wrong in the bond graph.
Sorry. R2, yes, that's right. I copied and pasted a little bit too quickly. Thank you. This one's wrong. So let's come to this point that this is wrong, all right? So we aren't really there yet, but it's good to have it in the right way. So that's the first step. Now, how would we measure the force going through this spring damper system? Well, we imagine the force kind of flowing through here, right? It's just this one force vector, and really it's a flow of the momentum decrease of this mass. So the force is going through, and the velocity, this is the velocity of the spring, would be right here, between these two things. We know from the principle of relativity that velocity is relative, so we look at the velocity of this point minus the velocity of that point. And this will be the velocity associated with this damper. What was that, R2? Okay. So the velocities are measured in a sort of a cross way here. Right? So you take the 2 points and you look at the difference. And the force is measured in a through way. The force we imagine flowing through the link. You follow that? Here, the situation is reversed. Where's the force? Well, it's a joint voltage on both the spring and the damper, so it will be over here. This will be the force, which is the voltage, right? The potential drop. So the voltage is measured in a cross way, and the current is measured in a sort of through way. We see this current going here, then splitting in two, right? It's a little bit bigger, and coming together again, and then it's flowing around. So not only are series have correspond to parallel, but also the variables have a different meaning. We talk about a voltage drop, and we talk about a force going through somewhere. So the member may be in compression or extension, and we think of the force is flowing through, all right? That flow is the flow of momentum, of course. And we think of velocity as sort of a cross, a relative. We look at the relative motion. So we think of the level of the velocity as being high. We don't think of the flow of velocity. It's a little bit silly, you know? So when you get a speeding ticket, he says, well, you're speeding at the level of this, 150 kilometers an hour. He doesn't say you're speeding at a flow of this. Huh? Okay? But a current is flowing at a particular rate. So the way we think about these circuits is very, very different. So we're all trained to see them as exactly the same, but once you think through the details, you realize this is very confusing. All right, the intuition is quite different. So when you work through the economic engineering problems, you'll see that you'll have the same problems, you know. Depending on the perspective you take, something is going to feel naturally to be a flow. You know, so if you have goods, you can think, well, they flow naturally, I see them going. But you can also think of a want to flow. You know that a want is the speed at which you're crediting. So you can think of the cash flow as flowing. A lot of people, especially in finance or accounting, will take that attitude. And they'll think of demand not as being a flow, but a level. You know, say the level of demand is really high for apples this year, right? They don't say the flow of demand is really high. Okay? So it's confusing. So economists, and also in real life, will switch between the two analogs all the time. And we do this kind of naturally. And when we think about storage, then we really think about a flow going into an inventory. And when you think about demand and I elements, we want to think about the level of demand or the level of supply, right? And then we book the cash flow, right? Or the money flow, or the flow of credit, I should really say. And we book our debits. And we can see them flowing into our profit and loss statements. So this is a major, major problem when we're doing, not a major problem, it's actually great because it allows us as engineers to unify these two approaches. The regular kind of supply line approach where you're thinking really of the goods flowing Okay, that will be an approach that, say, Roemer is taking more. But you can also look at more financial things where you think of the money flowing, which is more what Brit is doing with Rabobank. Rabobank is not thinking of a flow of goods at all. Okay? So what we need to do, and what this lecture will be about, is to kind of sort out these differences and give you the kind of realization, and perhaps we can talk also a little bit about what is a natural terminology, so to describe both situations. You know, so there's a lot of businesses say yours is real estate. It's not so clear. Are they looking for the flow of houses, or are they just looking for the demand of houses? I think probably they're looking at the flow of money and the demand for housing, because it's so centered around mortgages and other things, which is the perspective of the bank, right? And the perspective of the bank is kind of imposed on the customer, and he starts thinking of it that way. And some projects people will switch. You will see maybe these supply line guys will switch. They have an accounting department and they just switch. All of a sudden they started looking at cash flows, you know, and they turn into a different type of monkey, you know, than the inventory monkey. All right, and these managers sit and they switch all the time, and somehow they keep it straight in their heads. The same way you may keep straight in your head the difference between in a mechatronic system between the electrical circuit and the.
Oh, ik denk dat je even de...
Oh, wacht eens eventjes, ik kan gewoon dit niet helemaal eruit halen.
Ja, ook een kabeltje.
Zeg je?
Een kabeltje.
Ja. Een kabeltje laten en de apparaatverwisseling. Ja.
Zo slim.
Zo slim.
Hoe gaat dat ding eruit? Maar ik moet draaien.
Draaien. Het is een mechatronisch systeem. De volgende site staat de bondgraaf van de fabriek.
Ik weet niet of dat makkelijker is.
We hebben het in ieder geval geprobeerd.
Het uitsluit van de volgende keer.
Ja. Heb ik vergeten waar die in gaat? Line in of
Nee, Mike.
Mike natuurlijk, ja. So you should be able to hear me now?
Yeah.
Good, sir. Thanks. Now, after I talked about all of this, now you understand how these work. Now look at the bond graph, all right? Now the bond graph has no such problems, right? The bond graph just does it in one way, and you'll see here's the I element, that is exactly this mass. The C element, that is the spring, right? It's a lot of the terminology is borrowed from the electrical domain now, although I corresponds to inertia, it just so happens to be also equal to an inductance. Okay, and then these R elements are the resistors, or here the dampers. So I think I got this right. Yeah, I did, except for the causality. We'll talk about the causality later. I can talk about it. The causality just tells you what way the force is working, right? So of course the causality of the mass is this way because you have to push the mass. You can't give it a velocity. But a spring you can't. So the demand, you change the demand by changing the price. You know, you don't change the quantity. You have to bid it up and then you get stuff. All right? And here you change your inventory by flowing stuff into it, right? You can't just say, hey, I want to improve my convenience of this. And these R elements, they can do anything they like. They're just fees that you got to pay or other expenses. But the causality will come from the way they're wired, because there's only one way to get this thing right, is the masses, you gotta increase demand by increasing the price, and then, the fees you pay will cue off on the resulting sales amount, okay? And here it's the opposite, you increase your inventory so you get a higher level of desirability, now, and this level of desirability, the maintenance of the quality of that is what cues off all the expenses that you make on the storage, all right? So, now, although it looks from this figure that bond graphs do not care about this particular way of doing the variables, in fact, the way they talk about them, it does. It's all built on this electrical analog. So this can be quite confusing. And so you got to know about this. So let's spend some more time in analyzing the situation of this difference of what is known in the literature, in engineering literature, as being through and across variables. Okay? So what's the difference between a through and across variables? Now, in the mechanical analog, a force is a through variable. You see it going through all the members. If you link them together, the force goes through there. Okay? The across variable is the velocity. You take two endpoints and you look at the difference, so you do it across 2 points. Okay? So, in the electrical analog, the voltage is a cross variable. You look at a voltage drop over an element, and the current is a through variable. The current goes through the wire and through the elements. All right? Now, what is this in economics? And how do these work together? So here we are, we have these through variables, and in economics, also in engineering, you'll see words like a flow. So a flow of goods, it's a through variable. If you look at a flow of credit, it's going to be also a through variable, right? So Newton famously called this force the flux of the momentum, and he invented this word for this dot, which he called a fluxio. So you see that Newton is the one who told us that force is a through variable, and that's why we in mechanics we just call it the force a through variable. All right. Maxwell did it for electricity. I think it was Maxwell. It was maybe Faraday. He had the other picture in his mind. But electrical systems, who knows? What is flowing, right? Is there really electricity flowing? People thought there were things called electrons, but it turns out they're not moving at all. It's just something abstract that is moving, right? It's just a way of looking at it, right? You can also think of the magnetic field as moving, but that's just not how Maxwell did it. I think Faraday, if you read him, he thought of the magnetic field as actually having these flux lines, right? And he called it the magnetic flux, but whatever. That's not how it worked out. So the mathematical idea of a through variable is out of a vector, right? So you see a flow, and at any one point, you say, okay, it's going that way. So often we actually think of a velocity that way, right? It's just is going that way. So and the cross variable is more like a level. So you have like these two levels, right? So and there's an up level, and you say, well, it's like a gradient, something that you overcome. So you overcome a voltage drop, right? Or you have to somehow overcome this velocity difference. So it's a little different idea, and there you'll see words like level, like the level of demand, or a gradient that you have to go over, or a drop, right? And mathematically, we think of this as something that's called a covector. It's not something that's much used in engineering. You see it in a lot of differential forms. But rather than going along a path, you imagine yourself walking over a big mountain, and you linearize it, and you flag the uphill direction, and that just tells you like a local linear approximation. All right? So there's just some mathematics that we keep in track in our minds. And then when we put them together, when we multiply, you may think this is just a multiplication, but really it's not, right? If you have two vectors, this will be some inner product. Alright? Yes,
But like in mechanics, the vector and covector thing is switched around, right? Because the force is a covector and the speed is a vector.
yes.
All right. Okay.
It's a little weird, right?
Yeah. Sure. Okay.
Right.
Yeah. Okay.
So why is that? So V is a covector, you say, right?
No. V is a vector. Because
Yeah, but really, in our minds. But when we calculate, say, this integral, right? You'll see this is the kinetic energy. This is the critical integral, right? Then this thing here is the covector. Or if we calculate momentum, this is even better example. How do we do that? We do this, all right? Okay?
Yeah.
And then, oh, this is a not so good example. This is telling you,
But this doesn't say a lot because just integration and
no, it says something, but. Okay, so the answer is it's confused.
Yeah, they're dual, so it depends on the context probably. But I think usually we regard velocity as a vector, at least from the
Yeah, but often we regard force also as a vector. We don't really care.
Although I think physicists like quite consistently call it a covector if they
Force.
Physicists, engineers know.
No,
Yeah,
actually,
but why do they call a force a covector? Because they look at this thing. You see?
yeah, and actually you can call it a vector because it lives in a vector space. But
Yes.
Yeah.
So they call it because they look at work. So if you look at work, it becomes a covector. All right?
right.
So this is what you would call a force. All right? But if you look at kinetic energy, force is a vector, you see? Because the velocity is a covector, and you do it along the lines of the force, you integrate this, right? Because this dp, you got to know how momentum is changing. And that's precisely the line of the force, okay? So when you do this integral, force is a vector. Okay?
Isn't this really that you like do this integration in the cotangent space and that the v acts like a linear operator on the cotangent space? So you would call it like a one form, but like from the other perspective.
Right.
And then maybe we can.
The thing is, you're doing really this, you know?
Yeah, sure.
Yeah.
I don't want to
This
make
is
too much
equal.
fuss about this because it, like
This is
we all
this
know
inner
what we're
product,
talking about,
right? So this inner product, right, you replace by the
Yeah.
saturation operator, and that is power.
Yeah, I don't want to make too much fuss about it.
Yeah. So for the rest of you who are normal, this is just a bunch of mathematics, right? Yeah. And the thing is, this multiplication, which is really not a multiplication, but is a dot product, this is what forms the action between the vector and the covector in a very natural way when you want to do differential geometry, right? So the problem is this multiplication is really not correct because you have vectors, but even this dot product is not correct because you may not have a Euclidean metric, you know, so you don't have a dot product, you can't do any projections. So as you know, in the Edgeworth box, we don't have a metric, we don't know what a cosine or an angle is. And the only way to do it correctly is through all this differential geometry. So that's what this discussion is about. For now, it's just important to get kind of the picture in your mind, you know, how this works. And you're allowed to switch, and that's the whole point, of course, Emil. The fact that you can switch all the time is what makes this so handy. You can switch between electrical and mechanical. And in fact, if you have a zero junction, you may look at it quite differently than a one junction. You know, you just decide to do that. You know, in an inventory, you will think of the goods flowing in, and if you have demand, you will think of it as a level. You know. Okay, so you just keep switching perspectives. All right. So.
But in the electrical domain, this discussion doesn't make much sense, right? Because their power is the product of voltage and current, and those are both scalars.
Well, they're not really, because if you look in space, they certainly are not scalars, you know? And you can have an electric field not just going through wires, you know, electricity with wires, it can just go through space, right? Like an electromagnetic radiation or something.
A voltage is a scalar quantity.
No, a voltage, energy is a scalar quantity. All right? Now, energy is the scalar
Voltage
quantity.
has a direction. So it's
Yeah.
from minus to positive, but you can also switch it around.
Yeah, so that's a good point. Well, but you know, voltage has a direction, you know? What is voltage? Voltage is the change of the magnetic field, huh? Right? So it's a vector. You know, here. So if, you know, if it's a vector that's pointing along the magnetic field lines. So that's the answer. It is a vector, right? Or a code vector, depending a little bit. If you look at if you mark off areas of equal increasing magnetic field, you see, huh? Energy is the scalar quantity, and voltage only acts on current in order to get energy. You're silent, so I'm wondering whether I answered your question. Huh?
Yeah, I'm not sure this is right, but maybe I'm just gonna let it go because I don't. I'm not 100%. Sure. I'm not sure enough to go into a discussion about this, so I'm just gonna let it go. But yeah. I believe you are wrong, but I'm not sure.
Yeah, I think you should check this, and I think you will see, for instance, that a voltage, if you look at the voltage being a change of the magnetic field, just like a force is the change of momentum, right? Now, a change is always a vector because you have to give the direction, right? And the increased amount. Okay? So there's a change along a path, and then this is this force, or you can look at a change, you know, in the uphill direction, and then this is it. So it's always a vector of change, a rate of change. Okay? That is really if you study it, you'll see that's the argument that would, that's the definition of a vector, you know, that's a rate of change at a local point, all right? And that will convince you. Say like current is a vector, right? And then voltage and current, you just take the inner product of two vectors and you can scale it, okay? And that scalar is energy. So the idea is it's not such a bad question. Energy is the same for all domains. You know, it's just a scalar quantity. But you can think of the voltage as a force in some electrical direction. You know, and current as some velocity in some other weird electrical direction. So it's a vector because it has a direction, right? Notice the word direction. So it is a vector. So the idea of these two and cross variables is that you can choose whatever you want, but in the end, why doesn't it matter? Because you need one or the other, and they act together to give you power. And power, if you integrate it out, gives you energy, and that's all that's going to matter in the end. And these bond graphs, they focus on the power that's in there. So they don't really care what it is you multiply, okay? So they'll put the signals, you'll put the signals next to the bond, and then you can choose whatever you want. You can scale them the way you want, but you can't choose the way you measure power because that's the way it will communicate with the other bonds, all right? Now, let's just go through this. We did some of this before, but here I just kind of summarize what's going on. So here's the force. Why? It's a through variable. Why? Because Newton told us it's a flux, which is just a ladder for a flow of momentum. All right? So it's flowing through the links. In electrical, it's an across variable. So this stands for voltage, because we talk about the voltage drop over an element. So the voltage drop over a resistor, you know, doesn't need to be a drop, of course, but this is how we talk. In economics, we can talk in two ways about what a want is. So these are both wants, or a desire. But you can think of it a flow, the flow of money. So the way you, what do you do when you want something? You start bidding it up and you say, what is the want? Well, that's the amount I'm willing to bid. I'm still bidding here. I'm flowing the money per unit per time. So therefore I'm wanting, you know? So you think of it as a flow of credit, and that's how you book it as an accountant also. But you can also think of it as a desirability level. So then it's more a level variable. So when you have inventory shrinkage and stuff like that, you know, now the quality just goes down. And what do you mean by that? Well, you're saying why the level of desirability of this thing goes down, and therefore I can model that as a voltage drop or a drop in the spring force. So you think of the spring as being slowly against the damper, slowly relaxing. So you're dropping, as it were, in the force level. Okay, so then it's more the level of the force. Okay. So think about it. You can think about a want in two ways: as a flow variable or as a level. So a level of desirability and the flow of credit. All right, and both are valid. And the same is true for velocity or current. Right? So for us as mechanical engineers, the principle of relativity tells us that velocities are relative. So you can only measure one velocity relative to another. Okay, so it's an across variable. In fact, any velocity is always relative to an inertial reference frame, which fixes one's particular velocity. Again, the current just goes right through. And here we are. Yeah? So we can think of the quantity demanded as a level. This is like the level of the quantity demanded. Okay, and the demand is high. What do we mean? We mean that this stuff is being sold. You know, yeah? Or what? We can easily imagine that what does it mean for this stuff, for demand to be high, is that if I look at the market and I see, well, it's flying out of my inventory, then this flow is huge, you know, right? There's no difference, right? I mean, we do both. In fact, what I tend to do is when I talk about demand at one junction, I try to think of it as a level, right? And indeed, with the one junction we'll see is associated a velocity. So it's at that level, the one junction is operating, okay? And this one, I tend to think of velocity as a flow because it's flowing into here, right? And I think of the economic force as a level, the level of desirability that's maintained over the assets that I have here in stock, okay? And clearly here I think of the want as a flow, that's what this is saying, so it must be some flow of credit. I'm just bidding up the price, right? And how do I bid up the price? Well, I'm crediting or debiting my accounts, right, at the bank, right? So I tend to switch as well. So this is one of these issues. It's really confusing until you figure out what it is, and then personally I have some feeling of relief then, because it's somehow, the fact that it's so muddy clarifies everything, you know? It's just that the situation is slightly different, and then I just have to know to start reasoning slightly different, and I'm okay again, you know? I feel comfortable. And it fits with my everyday thinking of what this is. So whereas an electrical engineer, he can't do otherwise. I talked to a friend of mine who's a very good electrical engineer, but it's not possible for him to see that current is a level, or that voltage is a flow. And his brain won't do it, you know? Okay? And there are mechanical engineers who have trouble seeing that a velocity is a flow. A little bit less because they kind of see it in math with an arrowhead, but they also see a force with a vector with an arrowhead, you know? So as economic engineers, we just got to be agile to take both perspectives depending on what our field, what our application is. Okay. Clear? Good. I see some nods there. Only Ozai is not satisfied, but we'll have to deal with that. Huh? Okay,
I have an argument why current cannot be a vector, but I'll leave it for Thursday.
good. Yeah, let's do that. Thanks. No, it's good. No, these questions are good and these arguments are good because it gives us Quinn and I a chance to show that they're wrong, you know, like, huh? But no, that's not true. I mean, sometimes you actually learn something, many times. So, with this in mind, what I want to do is establish the terminology that is used in bond graphs. So what bond graphs try to do is they try to take an in-between kind of approach and make something that's palatable for everything. Now, from this discussion, you'll see that's really not very possible. So what ended up going is that they drew more heavily on electrical engineering. Now, I'm a little bit surprised by that and not surprised at the same time. I happen to know the guy who invented them. His name is Hank Painter, and he was at MIT when I was even there. You know, he was at that time a pretty old man, and he was a guru. So when I say no, I saw him walking around there in the corridors, and people say, "Ooh, that's our Painter." Huh? So I didn't know him very much, but he was a mechanical engineer, right? And but for some reason, he was one of these better mechanical engineers because he uses things from chemistry. This is where the word bond came from. So he thought of it as bonding together. And he used a lot of stuff from electrical engineering. So he came up with a way of describing that is pretty agnostic, as one would say, you know? So not very religious, you know, not adhering to one thing or another. And also something that we, you know, that we like. But nevertheless, you see, the velocity is called, so they have general, so here I have my usual thing, mechanical, electrical, economic, and I have this new category called general, all right? Generalized names for these signals. And in bond graphs, you use this generalized terminology, so instead of force or voltage, you talk about an effort. Right? This is a nice word, an effort. And instead of talking about velocity and current, you talk about flow. Now here you see, this word flow immediately means that you're using, you know now, this analogy. Now the effort, I feel also, an effort is a one form, you know, because an effort to me, if I climb up a mountain, I will get one of these hiker's maps and you'll see all these level lines of these mountains, you know, going up, you know, they'll have here 10 meters or 20, you know, whatever. And these level lines I can approximate. And then the vector is how fast I'm walking, and the mountain itself I see as a gradient, you know? And the effort is not in the way I go by time, but how much I have to climb, right? So how far or how close together these gradient lines are, right? The level lines of the mountain. Huh? So for me, this is a one form and this is a vector. I see it flowing, huh? And now, I happen to know a little bit more. You can also have a one form that flows, and what you do is you have two level lines and they go like this. So you can all fix it, okay? Yeah? They're called twisted one forms, and they have twisted vectors, and they're little line elements, but instead of a direction like this, they have a direction across, okay? So this is for the differential geometry freaks. You can still hold on to this and use your vector, covector, I think, by using twisted. But for the rest of us who are just normal people, huh? Maybe not including me in this rest, it's clear that the way bond graph is thought of is as the quantity of the commodity per unit of time is as a flow variable. They see it go as a flow. So this can be confusing. Especially when you think of the quantity demanded. Is the quantity demanded a flow? You don't feel it, you know? So keep that in mind. The word to me that comes more closer to being a flow will be the volume, you know? So what they mean by volume is, of course, not the volume of a cube, but what they mean is the volume, what we would call the volumetric flow rate, right? Okay, so on the stock exchange, you will see daily volumes, And this is just not the volume of the room up there, you know, but it's the amount of shares that trade in hands, right, per day. That's the volume. And Jaap also, he talks about the volume, doesn't he, Roemer? Huh?
Yeah, it does indeed.
He does indeed. So in practice, when you take the stuff is flowing perspective, which is at the stock exchange, right? It's not the bank, but the stock exchange itself. They see the shares flowing, changing hands. Okay, they will not use this is the quantity demanded is high at the IBM post. You know, they'll say the volume is high. So I feel this is a nice kind of flow variable, and this will be more of a level, you know, and a cross variable, the level of demand. All right. So please think of your head if you don't feel that, or you have other words that you think are better. Huh? Similarly, for the effort, this is the force or the voltage. We've always been talking about the watt, and I see these watts kind of flowing. You know, I have to think of it as a credit, and I say, you know, my watts are being communicated to you. You know, and they'll meet. This is where they meet these watts. You know, I see them meeting each other. You know, huh? But when I talk about desire, I would more think of that as a level. All right, it's somewhat of a similar word. Desire is maybe a little stronger, but in economics, you see, Marshall uses this word want, but Samuelson in his text says desire for the whole thing. He just gets rid of the word want. I don't know why. So I feel that's more a level variable, and especially like the desirability. You know, you don't say demand a wantability. Huh? I don't know how it would be in Dutch, but behoefte for me is really a want. It's a flow of something. But what is a level, a niveau van the, I don't know, I can't think of something right now, but
Verlangen.
what?
Verlangen.
Verlangen, ja. Ja, verlangen. Ja, verlangen is desire.
That is desirability.
Huh? Yeah. Okay, so much for these effort and flow variables. Here, for completeness, I just put in the momentum position. They just call this momentum and position. So here, they really take the mechanical thing. They don't call this magnetic flux linkage, right? And they don't call this the charge. And this corresponds to our price and stock. But also here, there's a little different perspective. For the mechanical engineer, the momentum is something that's contained in a mass, right? But, you know, so it's like a charge, all right? So you see it flowing in and it's contained in it. It's like, this is how they thought about it. If you read Newton and others, the time they thought about, you know, the force, where did the force go? Well, it's contained in the mass, that is the solution. But we don't think of the deflection of the spring as being contained in the spring. This is kind of ridiculous, you know? Huh? I mean, it's more of a level, right? Huh? Okay. So, whereas the electrical engineers, they really see this current flowing in there. They see little balls kind of flowing in, little black balls, is how my friend describes it. And it's kind of flowing in there, and they're charged up, you know, like you would charge, I don't know, a truck or something. Huh? And then this magnetic field, they would think of it more as a level, right? Now, a stock, if you have some inventory stock, there's really two ways to think about this. One is the level of the stock, you know? So if you do an inventory check, you just go and measure the levels, right? So you go to your warehouse and you measure how high it is or how many boxes you have, so it's a level, you know, inventory levels are high, right? Huh? You can also think of it as a big box and you just start throwing in, you know, let's say it's, yeah, we have a lot of stuff in inventory, right? It's like a charge, I go charge up, you know, my warehouse is chock full, you know, and then you think of it as being flowed in, you know, okay? So we switch a little bit on the perspective. okay? Whether it's a level, right, or whether it's a charge kind of thing. Huh? The same with price. You think of price, if you think of price as being a credit that you make, or a debit that you book in your things, well, you really think of it as a flow, a total flow of things. Huh? All right? If you think of it as a willingness to pay, also it's somewhat of a flow. All this willingness kind of flowed into you over time, through your wants, you put it all together, and there you are with all your willingness, and it's right into you, right? Huh? But we equally talk about the price being at a level. You say, well, the price level is pretty high. I'm sure in the housing market we do this all the time, price level is this, is that, So then we switch again, right? Huh? And we don't really see it as, we see it more as a flux linkage, right? The total magnetic flux that is come in, the total amount of voltage. So the voltage, is you have all these voltage drops, and they all add together to give you a total level of the voltage drop, which is the total magnetic flux linkage over time. So for everybody but Ozai, that's clear that it's then a vector, right? Okay. So these are the signals that we have, and this is the terminology. What's the next slide? Yeah, so let me do this slide, and then the rest we can do after the break. All right? So let's put this together. So these signals, they have to be transferred from one place to another, right? So when you do a transaction, you have to transfer your desires or your wants from one person to another. You have to communicate that, okay? And when you commit the transaction, you have to exchange the goods, okay? So the things that are communicated are both the effort and the flow, right? So this communication in bond graphs is done by this type of arrow, right? So we list the effort here on the top, the flow at the bottom. There's some kind of terminology, convention for this. I don't really care because the software just does it for me. And then I'm told that the software knows what it's doing. And so this bond graph can communicate, this bond can communicate between these two elements, A and B, in this way. And it's quite abstract way. You can imagine how this goes for an economic system. All right? You probably already have. And of course, if you multiply these two together or you saturate them, you get the power, right? That is. Now, what's that in a mechanical thing? Well, if you put things together in a mechanism, you already know that. You have to provide some link, some rigid, massless bar that you put there, right? So this thing is rigid and massless. So massless means that it's not an I element, and rigid means that it's not a C or an R element, right? Because both of them have to be able to contract or extend, all right? You can't do that, it's neither, it's not doing anything, right? It's not contracting, it's not extending, and it doesn't have any inertia, right? So that's the link. Just a piece of metal weighing nothing and being infinitely stiff. Something you're very familiar with, I'm sure. At least in the software and the pictures and the books. What is this in an electrical system? So here you can see the force will go through, right? And the velocity is just across. Of course, the velocities are the same. So this will maintain the velocity difference of 0. So you'll see it communicates a velocity from one place to another. And it also communicates the force by flowing through. Now, this is in an electrical system, this is called a port. Now, you see that here the current is a through variable. So you'll see this current going like this. So that is this velocity that's the same. So the difference between what's going in B and out of B is 0. Right? So you can see how you can do these across variables doing a through variable what the correspondence is, but you'll need two terminals. All right? Okay? Here also there are two terminals, one in here and one there. Except the one we look at the difference, we look at both at the difference, but we imagine them to one to be across and the other to go through. All right? Instead of the voltage going through, the voltage is now across these two terminals. All right? And this is a port-based modeling works this way, where for every link in a mechanical system, you put these ports, and now you can communicate. This is some hideously complicated electrical system, and this too doesn't matter, you just link them together. That's called port-based modeling. So you have links, and you have ports. Now, what do you have in economics? So you'll have some kind of, well, how do these transactions go? Well, they'll have to go through some trade network, right? This is exactly what trade is. So you exchange the goods, you exchange the money. So I just typed in trade network, right? In Google, and the first link was this thing here, right? So here's a trade network. So it's got tons of these little links, right? Boom, boom, boom. Here's some cities, Saudi Arabia, it says here, United Kingdom. Right? So a trade network, what does it have? Well, it has links, trade links. It has ports, airports, regular ports, So the terminology is not so different, This is kind of a surprise, but maybe not. Maybe this whole idea of things flowing and stuff, and it's not so in electronics and mechanics, it's not so different to how we think about economics. Okay? So think of these bonds as either links or ports, but you can think of this, a bond will be a little bit different. That will be a financial contract between two people, but link and port, you guys have roads, you can all kinds of a whole network. This will be a whole network, and here you can also create a network, with all these little wires, Okay? So electrical network and a trade network, they're really very similar. Okay? And with these bond graphs, what we can do is we can use this notion of a bond and then show how the trade will flow, how the network will function, all right, between the different places where demand is, where supply is, where the storage is, where the different fees are being charged for moving it from one place to another or for storing it, etc. Right? Okay? Of course, there's going to be transformative elements. We'll talk about those too. How now you go from some raw materials to some finished goods, and nevertheless, those all have need that trade networks, etc. Okay? For now, just see that these bonds are just a way of creating these networks, and whether they're electrical or mechanical systems, this is the way to go. And surprisingly, the terminology is very similar. I think I want to take a break right now, and then I have a bunch of other slides that we can go a little bit quicker when this is sunk in. And I'll see you in 10-15 minutes. Okay?
Max, goed.
Even kijken. Hoe kan ik nou dit ding verder?
Nu kan het.
Nee,
Nu kan het.
blijf nee.
Mij lukt het wel. Probeer nog eens.
Oh, no. Okay, so let's get started again. We left off at the bonds, and what we're going to do now is talking about other elements. Now, what I want to do is, rather than start talking about the elements, first talking about a junction. And the first junction I'm going to talk about is a one junction. Now, a bond can be thought about as really as a one junction. Here's a one junction, and rather than three bonds on the one junction, you put two. Now this is equivalent to a single bond, right? But we now have three 3 bonds on this junction. So what is this? Well, rather than explain this theoretically, let's just look at some implementations. So this little card here is probably the best, the easiest to understand. So if you would think of this card, you can imagine your mass spring damper system. Let me another color. The way you would do it, you would attach the mass here, and then say a spring there and a damper there, and there'll be the wall there. All right? So rather than just link them together, you put this little card in there, and what that assures is that you have a place to identify what the common velocity is between the spring, the damper, and the mass. All right? So this is a little massless, completely rigid card. All right? So this is the velocity, and there'll be these 3 forces on there, right? So in this case, F1 might be the mass, the inertial force, F2 may be the spring force, and F3 may be this frictional force. In the bond graph, you all take them all positive. And the minus sign take care of themselves. All right?
Split arrow.
What do you say? Sorry?
Just flip the arrow for the minus sign.
So this is a one junction.
Because causality is wrong.
God damn. That's right. I don't even know why there was a causality in here. There shouldn't be. This is not the point. Huh? The thing has no causality, so I shouldn't even have put a causality in there. There's not necessarily any causality. If there is, I should have 2, all right? Thank you. Problem with doing this in software is that you tend to copy and paste some stuff and turn off your brain when you're doing stuff. So don't do that for your thesis. Okay, what is it in an electrical system? Well, here I made a little electrical circuit. If it was a mass spring damper, this will be, maybe an inductor, a capacitor, and a resistor. But what you got to do to add up these forces, you have a common current, so that will be this thing going through here. And to add up these forces, to have these different forces, you'll just have the voltage drop over these 3 elements, right? So the entire voltage, the limit here, is the sum of these voltage drops. So the net force here will be the sum of those 3. So this is called a loop. Now this is just called a free body diagram, right? We just imagine that point as a little cart. So what do these have in common? Well, what they have in common is that here the current is fixed, here is the velocity is fixed. Okay? So there is just one single flow on the one junction. Right? And now the word flow is not so great. So I've indicated that with 3 F's. All right? And the efforts, they vary. But they have to add up to 0 because this cart is massless and this is a loop. So by Newton's 3rd law, and the 2nd law together, if you have a mass, you know that the net force has to be 0. And here by Kirchhoff voltage law, you know that the net voltage over a loop has to add up to 0, right? So this battery has to provide exactly the total voltage drop over the 3 elements. Okay? So now you know what these things are, right? In mechanics and electrical. So now what is it in economics? Right? I put this picture here of the town hall of Delft, right? And your first question is, what has this got to do with anything, right? That's not your first question, right?
I know it's the market that's in front of the town hall.
Yes, but it really is a town hall. So this market here, this is where you can, so behind the market you'll see, this here is a boating house. This is where they would weigh the butter. Behind here is something that's called the Waag. All right, and for you Belgians, that is here, that is where they would weigh the goods, but that's the same in
No, I asked the waiter actually there, so
What?
I asked the waiter there, so it's
Yeah.
a restaurant, yeah.
Yeah, because you can even see the scale.
Yeah.
It's right hanging there. So the goods would come in through the, well, I think it was the Zuidpoort or something, but it's the Binnenwaterstad it's called now. That's where they would come in, and they would come from the north, from Amsterdam through the other port. Oostpoort maybe. I don't know, a lot of them are gone. And then they would, all these canals would bring it to the back here where all the goods get weighed. Then they get transported to the market. So here you can see it flowing. So this is the flow. And they would get traded. So people are bidding and asking for these goods, right? And these bid and ask, they have to be cleared, all right? So you need some money in order to do this. And the money has to be managed by somebody. So there's two people that manage this. Really, there's only one. And this is the city hall. So this is where the mint was. This is where they would issue the money. And here, if you didn't pay the piper, you would be thrown into prison. So they had a little torture chamber here and all kinds of other things to make sure that the financial clearing was done. All right? And they're looking over the marketplace. Okay? These guys are in charge of the money. Now you would say, why are these guys in charge of the money? I can't have anybody in charge of the money. No. On the other side, you will know is the church. And that is, the symbol is God who ordained these people to rule by his grace to watch over the money, right? To regulate the money, right? So the flow of credit and debit was all done through little coins or accounts, and all the accounts would have to be settled here by the government, who had a little army of soldiers making sure that you didn't cheat, right? So the flow of goods was regulated through these, at the back here, through the Waag and the Boterhuis and different things, the goldsmiths, and they measured the gold, all right? You can see all their emblems still there. And the money, the financial thing was done over here. So in the economic case, what happens is you need to have that the wants or the credits, in this case, sum up to zero, meaning for every credit that there is a debit. Economically speaking, this is where you'll have the reconciliation of the wants. So the buyers come with the wants, the sellers come with the wants, and they have to be reconciled. And the way we reconcile it is with money, right? So these efforts, they have units of, say, florins, which they use, guilders, per barrel of butter, right? And per unit of time, right? Maybe per unit per second, because they're trading here per minute, right? Okay, that's where the credit is flowing. So this is what sometimes is called the clearinghouse, and here is where the different credits and the ones are being reconciled, and out of all that effort comes a flow quantity, and this is what economists call the market clearing quantity. So I put this there, market clearing quantity. So if here's a mass here, for instance, an I element, to measure the demand on this marketplace, then this imbalance of effort will make the price of the good go up and down, right? Until the quantity is reached, at which this is all brought in balance, and that's the quantity at which we say the market is clearing, right? And that market clearing quantity is the level that you can imagine as actually physically flowing here from the Boterhuis into the market, and then, through the different canals. The boter would come from Schipluiden and different places, and then move up to Leiden, other places, all right? Okay? Or herring especially. And Laken, which is the cloth. You can see all the emblems, it's pretty interesting. So this is why I put this here, is really not the marketplace itself, but the institution that does the clearing. So you can think of it as one junction as being in charge of the financial clearing of the market, right? So we already mentioned that these bonds, they signify the trade network, all right? Now, if you have a bond between two elements, it's just some people, doing some trading among each other, right? Hey, you can call that a market, but really you're not making a market, right? You will need to have three, and then more. You can add as many as you want. And you're just pumping through the goods. Everybody has this. The buyers and the sellers, they're all are subject to the same flow of goods. Okay. The amount bought is equal to the amount sold. All right. There's no reconciliation there. That thing is just pumping through. Okay. The total amount bought at this market. You see, the market doesn't store anything. So if you go to the market now, after the market is over, it's empty. There are no big warehouse things standing there. All right. So the market has to clear, has to physically clear. So it finds the flow at which it clears the the monetization of the ones. Okay. Similarly, in mechanics, this card takes the velocity that is such that balances the forces acting on it. Okay. Similarly, the current that flows here is the one, right, that will serve to balance the voltages around the loop. Okay? This is what you got to see. So you see that there's really two ways to look at this market. One is this physical flow, but I took the picture of this house. They're not really interested in this physical flow. They're more interested in the flow of money. How are these accounts settled? So in here are some accountants and other guys, checking whether that's being settled, right? Huh? And then from the other side, God looking on to see that this is all done correctly. Huh? Okay? So I like to think of this joint flow that is acting on this one junction as the market clearing quantity. The fact that the effort sum to zero, okay? I like to think of that as a reconciliation of the wants, or in a monetized way that the credits and the debits all balance to zero. Yeah? And even today, if you go to the CBOT or the New York Stock Exchange, you'll see there's something called a clearinghouse. And they take care of this business that the one junction should do, right? And you can see that these two conditions imply that if you look at the power of all bonds, the power over bonds is just the sum of the power over these different bonds. So here is the power of 1, 2, 3. That's, of course, this, by definition. But because the flow is common, I can pull it out of the summation sign. And since this is zero, you will see the power becomes zero. Okay? So energy is conserved. Another way, the total economic rent is conserved here. Okay? And this is, by last week we know, this is sometimes called the equimarginal principle. So this is the marginal increase of the rent, and that will be reserved. So you see, a one junction preserves, enforces at the same time the conservation of energy in the physical domain, and the conservation of the economic rent in the economic domain. So economic rent is not being allocated to the market. The market is empty afterwards. It doesn't own anything. Okay? Everything goes to the what is called nowadays the UBOs, the ultimate beneficial owners, right? The goods and the power can't be lost. The economic rent can't be lost. It has to be ascribed to somebody. So these guys can tax them, right? Okay, so one junction gives us this financial clearing. Clear? Then let's move on to the zero junction. If one junction gives you financial clearing, then a zero junction will give you physical clearing, right? Let that be. So here I put a picture of the VAC. Here you actually see the weighing scales. Maybe this is not the right picture. Well, this is doing the physical clearing to some degree, because physical clearing goes on here and on the marketplace itself, right? So you see all these flows going every which way, and in the end, the stuff that's not being sold has to be stored, and somewhere here there's got to be the storage rooms behind here. Really, this is where the weighing goes. That is to be sure that these different flows will add up to zero. Okay? Well, maybe there should have been a picture of actually the marketplace in front of it, as you would suggest, where you can actually see the physical clearing. So what does physical clearing mean? That, okay, the market comes in town every Thursday, they do. Before they come, the whole marketplace is empty. And you'll see the goods go in, they come in with their trucks, the goods coming everywhere, They don't use the VAG anymore. But whatever, it's all packaged and it's all labeled by the government, approved, EC approved pattern, so many grounds of this, blah, 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 right? And then you see it flowing every which way. And then at the end of the day, everything is cleared up and the little pieces of paper are cleared up and the market is as it was before. So nothing gets lost, all right? The goods are either restocked or taken away by the customers. So ultimately, on this physical clearing, the flows have to add up to zero, right? This is what happens on the market. But this way of looking at it means that for the market to clear physically, the goods have to have a level of desirability that's common to everybody at which this happens, okay? So here, people will have a store, say, of stuff, and I have my store, and you have a little bit more stores than I do or whatever, and what we're trying to do is figure out at what level of desirability is equal to us so that we can stop exchanging the goods. So it's a slightly different exercise. So rather than pumping the goods through and finding out at what level of the flow of goods, demand this settles, we now show up not with our willingness to buy, but we show up with our inventories, and we're going to see at what level we both find an extra apple equally desirable or less desirable. All right? Now, how does this work mechanically? Here is a zero junction mechanically, so you've got to look now at the difference between two of these little cards. And on this is a common force, right? So you just put something in between there that's pulling them together, pushing them apart. But the velocities will add up, right? So you'll have the velocity of the first card, the velocity of the second card, and then don't forget the relative velocity of the distance between them. All right? And those will add up, obviously. Okay? Here, this is, you think of a flow of goods, this is perhaps the easiest. So these are the levels of demand. So you see, the demand is a relative thing. So the demand of this guy with respect to the big world market out there, minus the demand of this guy with respect to the big market, is the relative demand between these two guys. Okay? You see? So we had some talk about velocity being relative, and I kept saying it's relative to some big market out there, right? So this may be a little market compared to the big, right? So we imagine that. And then Jonas, I think, said, well, you can have trade between two people. That's right. But still, both of them will be measured with respect to something else, and then we'll have to keep track of that third, the difference between them. And that's the excess supply of the one with respect to the other, right? This is the electrical idea. It's a little bit simpler in some ways, but maybe not, is that the goods are coming in, and from here and here into the market, and this is where they leave, and if the market has to clear, the market has to clear. So ultimately, nothing is stored on the market square, right? That's another way of looking exactly the same thing, and now the goods are a flow variable, right? So I like to think of this common effort here as not that it's a reconciliation of the ones, that the ones are somehow being reconciled, but they're coincident, they're the same now. Okay? And we do that by reconciling the goods, which is also allocation of the resources, because now we have the goods in storage, so we have an inventory of our commodity, and this is what you would call a resource, or maybe an asset if you control it. You know, it's probably better. And we're going to reallocate that. I'm going to give you some apples, and you maybe give me some pears or something else. I don't know how we're going to do it, but in any case, we'll make sure that, you know, our inventories are such, not that they're the same, but that these ones that we have, our level of desirability that we associated with it, the convenience, that those are the same. And this indeed is just storage, okay? So this is what a zero junction does. This is, in mechanics, there's really no law, it's just the kinematics of space. The fact that space can't be lost, you know, so two velocities are different, and their relative velocity has to be there. I mean, so the things have to get closer together, otherwise space is being lost, okay? In electrical engineering, it's just the law of conservation of charge, right? And yeah, it's just the law of conservation of these commodities. They don't just disappear. They don't just go into nowhere. Even if they disappear, we'll say they disappeared. So much was wasted or theft, or we ascribe it to something, okay? You can't just say, oh, these are goods that tend to disappear. No, they're stolen, right? How much is stolen? This amount. Okay, so we imagine them being somewhere and we've lost track of them. So we don't think of them as just disappearing, like a cloud would, you know? You have one cloud, another cloud, two, another cloud. One cloud just disappeared. You know, that's not what it is. Huh? Otherwise, this whole business of weighing at the VAT wouldn't make any sense. All right? And you can get energy conservation now, not in the same way. You pull out the common level of desirability, and you get the same equimarginal principle. All right? And here it's the same as on the one junction. If you just have a zero junction with two bonds on it, that's the same as just the bond, right? So all the bond does is just put through the flow and the effort, okay? The wants and the demand. What do these junctions do? They just start making the market, right? It's also called market making. You start adding more and more. More people can come in there. You can chain them together if you want. You can add the players. And that's what we'll do next. All right? Clear? You know, what I find weird is that these one junctions and zero junctions, when I think of these mechanical systems, I always have to really think about what's going on. There's also levels of extraction. It's never really clear. You just get kind of used to it. You say, oh yeah, there's a one junction, some of the forces. You know, it's a free body diagram. You get used to it. But here, when I say clear and I see everybody nod, I kind of know what you say. This is just really clear. You know, I mean, there's no way to think that this is not happening. You know, so there's something that I like about economic engineering, that things that you think you know so much better in engineering, all of a sudden when you give it an economic interpretation, it becomes really clear. You know? And I find myself sometimes at a point that I prefer to think of a force as like a want or something, or a credit, you know, than, you know, or a velocity as a flow of goods, just to make it easy for myself, or energy as being some economic rent, or momentum as being a price level that I have, you know. Then it helps me keep the variables. It's a weird feeling, so maybe you're feeling the same. I think it's what makes the subject attractive. At a certain point, you just get it, and then you get more than you used to get about the other stuff. All right, let's keep moving. We're making good. So what I want to do now is go through a couple of elements with what we have to know. We can go pretty quick. Right? So, because we did a lot of work. So you have these effort sources. An effort source is an element. It's SE, source, or SE for effort. So don't, just because the E comes after the S doesn't mean it's a source effort. It's an effort source. It's still a source. Okay? For all you Netherlands or Dutch speakers. And then what an effort source does is it imposes an effort. Right? It imposes a force.
Wrong again, right?
What?
The causality bar. The causality bar in this case. It should be on the other side.
Yeah.
right?
Yeah. Thank you. Yes, thank you. Thank you.
If you watch this video backwards, then it all makes sense.
Yeah, if you watch it back.
We can just redefine causality because they're all wrong. So
Yeah.
Yeah.
They're not really.
yeah.
Yeah, this is
Just okay.
They're just different.
it's terrible. Thank you, Max. Now, we're seeing that Max Grootman is getting it and Max Mendel is not really getting it. So there's still a difference. Thank you. So, what I wrote this as E of t, where you can think of this as a force, as a function of time. Why did I write that t there? Well, of course, all of it is a function of time, but I do that to emphasize that this thing is only a function of time. It's not that you can calculate it from something like this, which is also a function of time, but you can actually figure out what the function of time is. Here, this thing is specified only in time. This is what it is, and it's imposed on the system, right? So we talk about it as an external force, forcing forces sounds a little silly, but and maybe this external would be called exogenous, in economics, if it is really external. But what you do is something with some kind of potentially infinite resources and money is imposing this want. So something comes in, a big player, and he starts bidding, okay? Now we encountered this before when there was some fixed fee. So I had set this equal to a constant. It was a couple of lectures ago, I believe. So it was like a frictional force that I had, but it could be anything. Okay. Then of course he imposes this effort on whatever comes here, say a one junction, right? And then it gets distributed out. So if he does that, Max Brookman is totally right, then there's no way you can put the causality here. It's imposing this, okay? So this is like more wrong than wrong. And then the thing waits around and he sees what is the flow of goods that he's getting. And it's almost like he doesn't really react to that anymore because you see this effort is just a function of time and he'll just go on doing what he does best, is just keep bidding at this thing, okay? So he must have indeed infinite resources in order to keep that up. So in your systems, you'll see that, and I'm sure Koen will be able to give some good examples, like just for things you approximate that way, all right? I just have this fixed fee example that there's some very huge service supplier that just charges a fixed fee of so many euros per item per time. There you are. Take it or leave it. Okay? So the only thing you can really do is break the bond. That's the take it or leave it. And in electrical engineering, this is the voltage supply, right? So, and then this thing, they call it an EMF, electromotive force. So that's the force. Rather than a voltage, you will refer to that as an EMF. So the battery will supply an EMF. Okay? So that's quite a single. So this is an example. It doesn't need to be fixed. The fee can just be a function of time. Could be. So for instance, typically you will have an oscillatory, in engineering you will find, especially in electrical engineering, they'll do these oscillatory voltage sources, right? So this will be an AC voltage source. How do they write that? That's something like this, right? Plus and minus. So that's somebody who's bidding up, and then he starts bidding it down again, bidding up. It's not so crazy. A very big buyer. Now the company wants to first bidding up and don't want it so much anymore. In mechanical engineering, there'll be some cam, right? They do some cam, and then with the cam you can make it go up and down. So
But it's more like a flow source.
it's more of a flow source. Yeah. But it will be an AC effort source in mechanical engineering.
Yeah, just AC force.
Yeah.
So like an engine.
Yeah, like
It's not as constrained as a cam because the pressure can
Right.
still push the piston back. But like a
Right.
piston, you can see that.
yeah, like a combustion engine or something, or steam engine. Yeah, I can see, yeah, that's right. Yeah, I mean, in economics will be some big buyer, you know? This is what he's bidding. So, not so interesting. Well, very interesting, but like nice and simple. Well, most of these are now simple. This is the kind of the advantage that we did a lot of work. You know, we already went through these elements, so there is just not, we can just go fast now. All right. So what do I have here? An I element. Did I get the causality right? I think so. Yeah.
Now there's a double connotes in island.
Yeah, this means I. Yeah. Nice try, Joris.
Let's keep trying.
Yeah. So there, the effort, of course, is equal to the change in momentum, right? And as you know, the one there is calibrated to be a change in the willingness to buy or sell, right? So a reservation price change. This is sometimes called the inertial force or the Newtonian force. So it's electrical engineering, this is also sometimes called the electromotive force. It's like a little battery. I don't know, it's a want, but I love to call this just the force of demand, right? This is the economic force. Yeah, it's just the force of demand. So this is what people like Marshall would use, the forces of demand and supply. So why not, right? But you can call it anything you like. Then this is the relative velocity or the through currency, and this is just the quantity demanded for it. Right? So you have the force of demand and it pairs with the quantity demanded. And this is just the relative velocity of the mass. Well, this is the current going through the inductor. All right? So just have these flow and effort variables. You can use more specific terminology. That's basically what I'm putting here. So you have a little bit of a different feel. Huh?
And why do you choose to call it the force of demand and quantity of demand and not the force of supply, quantity of supply?
Just because this is more common. Huh? Huh? It could have been.
Could have been supply.
Usually people say demand and supply like they, you know, somehow demand is the phenomenon, not supply, you know? There's just no reason. Huh? I could have called it this force of supply. I could have called it the price movement, you know? You know? I could just call it a want. Or I could have called it a change in the willingness, you know? I could have, you know? Or I could call it the credit, the crediting, huh? You can call it anything you like. Eh? The same with this inertial force. You don't have to call it inertial. You can call it the Newtonian force, or you can call it, you know, the force without anything. Eh? The force on the mass. Eh? So these are just ideas, you know, to make it a little bit more, tangible and more specific. You know, this is just to show you that. You know, there's one way of doing this. Okay, this is the want, and this is the want of that, and this is the want of that, and this is the want of that, and it's a little bit like, oh, okay, huh? It's like saying, okay, there's a voltage, and there's no EMF as a voltage, and this is a voltage, and there's some terminology. They think of that as the electromotive force, you know. So it's not totally crazy to call this a force of demand because that's how Maxwell thought of this particular voltage. You know, he called this the electromotive force. This was the thing. This battery or this inductor In this case, it's the inductor. He thought of the inductor as providing the force, needed to keep these things moving, and that's why he called that the electromotive force, right? So you can think of the battery, the voltage source, as also providing electromotive force. It's kind of pushing it through the wire, right? Whereas the resistor is just resisting this electromotive force, and it's not really itself. The voltage drop there is not really an electromotive force. And here it's the same, like this is the force of the man, but that's of course going to be equal to the convenience yield or something if you attach this sort of thing. But the convenience yield itself is not a force of demand. I mean, it's harder to think because there's no market, there is no phenomenal demand of this, you see? It's just there, and then when you connect it to a market, you will see that it will imply a certain force of demand. So that's why I'm making these distinctions, because it allows you to kind of reason a little bit easier, But I'm not claiming either that these are unique or that you can't take something else or, It's just some ideas.
Very well.
So the quantity demander to me sounds good because look at the causality. This force of demand comes in, and then this is sort of a past participle. This is already done, so it will imply that it imposes this demand, right? So it is demanded. So boom. So. I kind of like the way the causality works, So the force of the demand leads to quantity demanded, right? You see? I'm trying to really, I'm trying to think really Newtonian and Maxwellian about these things, In this case, Newtonian. For me, an eye element is just really. The Newtonian analog of crossing through is better than, I don't like this electromotive force, and neither did Maxwell, because he's using this force notion, right? He's not using an electrical notion. He's not saying the change of the magnetic field, he's saying force, right? That's what he's imagining, right? Okay? You guys also clear with all that? Huh? Good. Let's, we only have 2 slides to go, so I think we can wrap it up.
7 minutes, 2 slides.
Yeah, but this is a C element. What's there to say? Like, I think I got a causality right. Unbelievable. Here, this is a C element. Spring force, right? Causality works out the other way. So this is a storage facility. So here, this is also a through variable. So I'm charging up my storage, right? So I'm supplying this Q dot, right? In response, the convenience of having this stuff is changing. I get more and more. I'm, oh, this is going good, right? So my force is reacting. My convenience yield is going up, right? Oh, I got all the stuff. I'm really happy, right? So you see the causality is just right. So the convenience is a result of the amount that you acquired, right? That you have in storage, you acquired. I didn't say bought, I just said acquired. I don't care now that you got it from a market or you got it in some other way, right? Maybe it leaked in some other way. You acquired it at a particular rate, that's this. You integrate it out, right? Your acquisition rate. Then you get the total stock you've required, and that will yield to you your convenience, okay? All right? So in mechanical engineering, it's no different. You take a spring, you start extending it at a particular rate. Because of that, the spring is going to give you back a particular force. That will tend to counter that. All right? You're going to charge a capacitor, and it's going to build up an electric potential to counter your business of charging this, Here you're charging up your inventory, and at a certain point you're saying, look, I got way too much, man. This is killing me, It's super inconvenient to have all this crap lying around, right? So Okay? So you see, it's very similar, and not only similar, it's almost easier, now? So here I said this is a want, of course, and this is a flow of goods, but here I just call it acquisition rate, just because you're acquiring these goods and you don't really care how. Huh? Okay? And the last element is the R element. This is really a little bit bipolar, or bicausal, as you'd say. It can go either way. So you either attach it to the market itself, okay? And then you've got to transport all these goods. You know at the market, there's the flow of goods that's constant. You can't, the level of demand at the market, you can't get rid of that, right? So all the costs go into not in losing that flow of goods, no, by changing the price, right? So the tax collector will need a little bit. How do you do that? Well, it has to get his margin. That's the value-added tax. He'll take it out of it. Then the weighing house at the back, they'll need something. They'll charge their margin on the price, okay? So the total price will be made up of whatever you get, plus all these margins they make, okay? All these service providers. And these margins are based on the velocity of the goods that's going through there, right? Okay? The more goods you're processing, the more value-added tax you'll be paying, all right? The more you'll be paying for the weighing services, etc. All right? So you take the flow and you calculate what the effort is going to be. So then the causality would be this. All right? And this is also what happens in mechanics. So you put a damper on a mass, what's going to happen? The damper will start being compressing at the rate implied by the velocity of the mass, but by doing so, it will reduce the momentum of the mass until it comes to a stop, right? So here is your system, here is your mass, and well, in this case, if I have the velocity going this way, this damper will extend, but it will do so, will take away the momentum, will be P dot will be negative, right? So it's completely analogous, all right? If you take an inductor and you put a resistor and you do this, it's just this resistor is going to discharge this inductor, so the magnetic field in the inductor will just take go down. So there'll be a voltage drop over this resistor. There'll be a friction force generated, and in economics you'll be charging a premium. Now in this one, you're turning it around. So this one, you have your goods in storage. All right. So now. What's going to happen, because you have them in storage, you'll have a certain convenience yield on the goods. Now, in order to maintain that convenience yield, that's the quality of your goods. They're not like wearing and tearing and they're not being stolen. You need to get some guards to guard this. You need some air conditioners so these things don't rot and all of this. But it's all there because you want to have a certain level of desirability on your goods. All right? So, what's going to happen is the friction there will serve to degrade the number of goods. Either some of these apples are rotting because of this, your air conditioner is good, or it's being stolen because the guards you have are not paying it up, I don't know what. So it works on the other way, all right? So this is the situation where you have the spring and the damper are put in series, right? So the force goes right through, that's the effort, and you'll see that what you'll get is the compression rate of the damper takes away from the compression of the spring. And in the electrical circuit, we saw that this resistor will discharge this capacitor, all right? So that's the discharge current or the compression rate, and that corresponds to the shrinkage of your inventory, okay? So this R element can do two things. And then if I then go back now to my first slide, you'll see that if you take a little time, you can now easily talk your way through the entire working of the system or this one graph here. Okay? So you'll know what this one junction does, the zero junction. This is your financial clearing. This is your physical clearing. This is the shrinkage you have. These are the premiums that are taken out. This is discounting the price. Okay? Here the price is being made. This is where the goods are being traded. And these are the storage units. You know now. This is what these guys who are selling herring, they just have in their truck or whatever they have for inventory. All right? So my time is up. So I'm not going to talk more about this. In fact, Thursday we'll be dealing with circuits, block diagrams, and how you can kind of fill this in and how you can make this connection. But with this lecture, what I've tried to do is at least give you the concept and the tools to think about all these various things that make up these bond graphs. Everything that's missing here are transformers and gyrators. You know, I could have put here an effort source. You know, I'll put some force here. That I still have done. That I will do next week. It's also a very interesting topic. Okay? Yes?
The only thing that isn't clear to me are the, how you call it, the causalities.
Yes?
The lines.
Okay.
When we put it in, and when not.
Okay. Let me take 3 minutes of the time to explain this. All right? So suppose you have a mass, right? Here, this thing. How do you get this thing moving?
By pushing it.
By pushing it, yes? So you have to apply a force, and then it moves, right? So what we say is, to get this moving, I have to push it. So think of this bar here as a hand, and it's pushing, right? So the causality is from push to motion, okay? All right?
Yeah.
That's what this is saying. Now, suppose this is a market, and you're showing up with your demand. How do you get a higher flow of goods? By bidding. You have to bid more. You can't just say, hey, I want more stuff. You got to pay, right? You got to pay more, right? So that's what you do here. You exert this force. So you translate your wants into an actual monetary thing and saying bidding up the price. That's that P dot, okay? And then what you get is a bigger flow, okay? What if you have an inductor? How do you get that to move more current? Well, you have to apply an electromotive force on it. You have to apply a voltage over it, and it will do it. Huh? You can't say, hey, give me a bigger voltage, right? Okay? Now go to this C element. Suppose you have a storage, and you got all this stuff, you know, the super income, so you're short. It's inconvenient to be short, right? Huh? How do you get yourself up? Well, you can't just say, hey, I'm changing my feelings about this, right? You gotta get more goods, right? Somehow you gotta load your storage up and then you're feeling relaxing. So what you do is you load in, and that's what this factor is, you flow in the goods, right? And then the convenience will change. Now the convenience is pushing, right? So this storage will be pushing on whatever is here. So that's why the causality is the other way, all right? If you have a spring, how do you get the spring to give you a higher force? You can't say, hey, Paul, I'll put a force on it, let's see what you can do. Not gonna work, right? You gotta depress it, right? And when you do, it will respond with a force. So you gotta depress the spring, that's what this Q dot says, and it will respond with a force. All right? Now, if you have a damper, you're gonna do either. You're gonna start putting a force on it, and it will respond with a velocity, or you can put a velocity on it, and it will give a resistive force, right? That's one is called resistance, and the other is called damping. Yeah? So it can do either. So which one? Which one is wrong? This one is
The right one.
this one's wrong, right? Yeah. So these are the two. All right?
Yeah.
Okay. So remember, in economics, you have to change the price in order to get a higher level of demand. And so that's how the causality is here. And here, you got to change your inventory stock in order to get a different convenience yield. All right? It's just the way it is. Do the other way around. We call it non-causal because it can't happen in time. One is the cause and the other is the effect. If you build non-causal system, you can try to do that in engineering. You know what's going to happen? Do you know? Can you imagine?
You get a controller.
Huh?
You get a controller.
Yeah. Yeah, but what happens if you try to do this, right? Well, things will have to somehow move infinitely fast, right? So if you want a mass to give you a different velocity, you'll have to somehow, put in infinitely fast, some humongous force, infinitely high force. So you will hear a big bang, right? And the thing will break because it can't sustain this force, all right? Huh? The spring, if you want to depress it infinitely fast in order to get the force in 0 time, right? You go faster than the speed of light, and you first hear the bang when you go through the sound barrier, then you will see the Doppler effect when you go through the light barrier, and then you won't even exist anymore because then you become light and you can't even go.
So don't do it.
Right. It won't work. It won't work. That's the point.
We lost 5 students like that.
Yeah. They got the causality stroke wrong, and we lost the student. You see? It just won't work. It's not physical. And in economic engineering, it's not economic. It can't happen in time. Okay? You got it? Yeah. So with that, you got everything now?
Yeah, I get it.
Oh, I'm proud of myself. Because this is not easy, this stuff, okay? This is not easy. All right. Thank you all, and I'll see you Thursday. Huh?